This video is going to be about problem-solving strategy, given a couple kinds of ways that a problem can be phrased. This problem is saying find the acceleration, and that tells us something about the best way to solve it. If we look at another problem, let's look at problem 5. Problem 5 is even bolded. Find the speed of the block when it has moved 0.5 meters. So these are two very common ways of phrasing problems in physics. Either find the acceleration or find the acceleration in tension, or find the speed when each object has moved a certain distance. Both of these are pretty basic kinds of problems that you might be asked to solve or that you might find when you're really seeing how things behave. But there are different methods that make it easy to solve each of these kinds of questions. Let's see how they work. So the first thing, if we're asked for acceleration, we know there's a famous law that says that the net force on an object is going to equal the product of that object's mass times its acceleration. If you're asked for acceleration, you probably want to use this method. The acceleration is going to be what you get by finding the net force and dividing by the mass. Anytime you are asked for acceleration, or maybe if you're asked for acceleration and tension, or to find a net force, a lot of times your best bet is to use this thing, which is Newton's second law. But we have another method, and let's see how it works. The second method is to use something called the Work-Kinetic energy theorem. And what does this say? The Work-Kinetic energy theorem says, again, if we take the net force, but we multiply it by the distance that the object moves while that net force is making it move, that will equal 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared. And I'm claiming that these two methods are totally equivalent. They'll give us all the same information. Just using this work-kinetic energy theorem sometimes will save us quite a bit of work, and this quantity, force times displacement, is called work. So work causes a change in kinetic energy. This quantity, 1/2 mv squared, is called kinetic energy. So where did this idea come from? Let's see. Well, what is acceleration? I know that acceleration is the change in velocity divided by the time it took that velocity to change. So that's v final minus v initial divided by how much time goes by, delta t. That's useful. Now, what if I want to know how far something moves? So I want to know what its position will be, x final, after some amount of time. Well, I can start at the initial position, and then what I'm going to add is the average velocity, how quickly it's moving on average, times how much time goes by. This can be rearranged to remind ourselves the definition of v average is the change in x over the time it takes to change, delta t. But v average also means another thing. How do I average any two things? I add them together and divide by 2. So let's suppose we started at some initial velocity, v initial, and ended after some amount of time at some final velocity, v final, and we had constant acceleration, so we're moving from one velocity to another during this time interval, delta t here. Well, I'd like to know what the average velocity would be over this time period as I go from v initial to v final. And here's what I notice. Imagine that this is actually Jell-O. All this in here is Jell-O that I've poured into an aquarium, and then I put it in the refrigerator tilted like this. Well, I would tilt it this way. So it finds level. It's mounted in the rails of your refrigerator rack, leaning against a wall like this. When the Jell-O solidifies, it's going to have an angle, and then when we tilt it back up, it'll be angled like this. So, with this angled Jell-O, what if I wanted to, now that the aquarium is level, get a level surface? Well, I could chop off this triangle right here and pop it down right in here. And notice that this triangle, I'm going to color it in really solid, would fit right into this hole. So that tells us that halfway between V final and V initial, that's where we would find the average value of the height of all that green Jell-O. But long story short, the average velocity, V average, is the average of V final plus V initial over the number of things I've averaged, which here is 2. So that tells us x final is going to be the initial x. Let's stick with I for initial. Is going to be the initial x plus V average, which is V final plus V initial over 2 times delta t. And x final minus x initial, I could also call delta x. So delta x is V final plus V initial over 2 times t. Now here is the good idea that someone had. I can take delta x and I can take A and look at what do they have in common. This t is a delta t, it's how much time has gone by. This involves dividing by delta t, and this quantity involves multiplying by delta t. So what will happen if I multiply A times delta x when this has delta t in the denominator, and this one has delta t in the numerator? Well, let's see. If I take A times delta x, that's the same as what A is, so that's V final minus V initial over delta t. And delta x is V final plus V initial over 2 times delta t. So my delta t's cancel, and now I have something with no time in it, which I really like. Time is always algebraically complicated to deal with. And now I've got V final minus V initial and V final plus V initial, and I recognize that's how my differences of squares factor, so I know this is V final squared minus V initial squared. And don't forget this too, V final squared over 2 and V initial squared over 2. So looking at this, I'd like a physical explanation of what this relationship means. To get that, let's multiply the whole thing by m. So ma times delta x is, let's pull these 1/2s out front, 1/2 m v final squared minus 1/2 m v initial squared. And do you remember what we call ma? That's just F net. So anytime I have a net force, if that net force acts for some distance, some displacement delta x, multiplying this force times this displacement, and more technically it's a kind of vector multiplication that we'll talk about another time, that is going to give me the change in this quantity, 1/2 mv squared. And I give this quantity 1/2 mv squared a name. This is called the kinetic energy. This is also kinetic energy. So I have kinetic energy final minus kinetic energy initial. So how do I change the energy? I do this thing. I exert force times some distance, and that's called work. So notice, if you're asked for A, you probably want to use Newton's second law. If you're asked for the final speed, these are final and initial speed squareds, you probably want to use the work-kinetic energy theorem, which is this: F net times the displacement is equal to the change in kinetic energy, or 1/2 mv final squared minus 1/2 m v initial squared. A lot of the time problems will start with this guy being equal to 0 because it'll start at rest, and then you'll just have 1/2 mv final squared, and that makes it really easy to solve the problem. So I hope that that helps with some of these problems.